Before solving another and quite nice example that requires the use of the generalized Hooke's law, let's take a brief pause and go back to a expression that I promised I would drive, and that expression has to do with the Young's modulus. The bulk modulus, which involves the Young's modulus and the Poisson ratio. So for this purpose, we need to introduce the concepts of volumetric strain as well as the hydrostatic stress. Okay. So what we would like to do is derive the expression for the bulk modulus in terms of the Young's modulus and the Poisson ratio, and that relation was B equals E over 3 1 minus 2 nu. Okay. I know that any elastic constant can be expressed in any other two for the case of isotropic linear elasticity, in this case B in terms of E and nu. And remember that this expression for B and together with the expectation that we expect it to be greater than 0 delivered the upper bound nu equals 1/2 on the Poisson ratio. Also at this point, remember that there was a relation for G equals E over 2 1 plus nu. That expression can also be derived, but you're going to do that as a side homework problem, and that can only be addressed after we talk about stress and strain transformation, which is going to be the topic of the next section of the course. So presently, this is something we can derive, and we're going to do that again with a simple experiment that involves a block of material. Again, not necessarily infinitesimally small. It's just a block of material. And let's indicate the three directions of the associated with the edges, x, y, and z. And there are three dimensions here. There's a length, there is a width, and there is a height. Okay. So we will try to calculate the volume change in the volume of this cube when we subject it to certain stresses. The initial volume, it's clear, the initial volume is L times W times H. And we are interested in the new volume after the deformation occurs, and the deformation occurs due to both normal and shear stresses. But remember that if I impose a shear stress, which I can depict over here in a two-dimensional setting, suppose I have here x and that's y, and this is an original, say in 2D, a plate, and now I'm going to apply a shear stress on a shear force on, if you like, on that block, on that thin plate in 2D, and it is going to deform to a new shape. And that's going to be the new shape, and the area in 2D, it will be the same as the area after deformation, right? Area after deformation is going to be the same as the area before deformation, and that's because the area after deformation is also height, this height times the base area, which is the same as the initial area. And now in 3D, if this thing did have some volume associated with it, so if this were in 3D, then the deformation of that three-dimensional block would also be preserved under shear. So in other words, in 3D, in fact, irrespective of what kind of shear deformations you have, as long as you have only shear deformations, it turns out the volume does not change for precisely the same reason that we are observing or making use of in this simple two-dimensional example. So, which suggests that volume change, 1, has to do with only normal stresses, and 2, I can monitor that volume change only through the change in associated with, if you like, normal strains. In this case, normal strains will have to do with the change in the dimensions along x, y, z axes, or in other words, in W, L, and H. Now, the second of these statements, that volume change is associated with only normal strains, is eventually a statement that is always true. The first of the statements, that normal stresses only eventually will cause volume change, is an expression that's based on our understanding of isotropy, because what we're saying is normal strain, which is responsible for volume change ultimately, is going to be caused only by normal stresses. But it turns out if the material is anisotropic, shear stresses can also cause normal strains and hence volume change. So ultimately it's true that volume change is only associated with normal strains, but only if it's isotropic, volume change is going to be induced by normal stresses. So having summarized that, and we're going to see the outcome of that summary in quantitative form shortly, let us now try to calculate the new volume of the block after deformation. And the new volume is associated with normal strain, so which means that the block is going to have a new length. Let's call that the old length plus the change in the length along the x direction, change in the length along the y direction, and change in the length along the h direction. That's just the new volume. And that volume is equal to LWH plus delta L multiplying WH plus L delta W multiplying H plus LW multiplying delta H plus terms like delta L delta W multiplying H, or delta L delta H multiplying W, etc. And finally a term like delta L delta W delta H. Now remember, we are not only assuming elasticity and isotropy but also linear elasticity, which means deformations need to be small. In other words, relative magnitude of delta L with respect to L and that with respect to that, etc. has to be small. In other words, we should have small strains. And therefore, all of the remaining terms, because they are of order delta squared and higher, in other words, we're going to see terms like delta L squared, delta W squared times H, or a term like delta L, delta W, delta H. These are all terms that are of at least order delta squared or higher. That we indicate like this, another use of the order of magnitude sign. And because now delta is small, we can omit this term, which means that the volume change is approximately equal to the first four terms that we have already written. So once we omit it, we can say that this is gone, and we have roughly V prime equals that expression. Let's make that a larger x so it's not a multiplication sign. All right, so then we can go ahead and calculate. Okay, let's also note that this is small deformations. That's where the observation comes from. And then let's go ahead and calculate delta V, which is V prime minus V, which is evidently equal to delta L WH plus L delta WH. And finally, LW delta H. And subsequently, I'm going to divide this expression through V, okay, that through V, which means I'm going to divide by LWH, okay. So L goes there, WH goes there, all right. L goes there, W goes here, H goes there, and L, W, H goes there. Good. So these terms cancel, that's 1. These terms also likewise cancel, that term cancels. Now here this is change in length divided by length. that's a strain, a normal strain associated with the x direction, so that's epsilon x. Strain associated, normal strain associated with the y direction and with the z direction. So change in length over length, our standard definition of normal strain. And on the other hand, here we have change in volume divided by the initial volume. So normal strain has no units, shear strain neither, but no units. And here as well, we have a quantity that doesn't have any units, plus it's associated with somehow normal strain. So we're going to use the symbol epsilon and put a subscript v to indicate that this is associated with volume change, which now defines us an equality or an expression for so-called volumetric strain. All right, so that's a useful concept that we eventually will make use of. All right, so the volumetric strain, change in volume divided by the initial volume, is only governed by normal strains, and that is something that we understand. And eventually now we're going to show that volumetric strain is only induced by normal stresses. In fact, through a special combination, simple combination of normal stresses. That assumption will rest on generalized Hooke's law in the isotropic form that we know so far. So now, for that purpose, let us first go ahead and remember generalized Hooke's law. Now, in generalized Hooke's law, we have the normal stresses related to normal strains. Let me quickly write it for you. So at this point, it's good to make small exercises to remember what that form is. So epsilon x 1 over E, stress in the corresponding direction minus the Poisson effect, sum of the stresses in the remaining two directions. So 1 over E, sigma y nu, sigma x plus sigma z, 1 over E, sigma z minus nu, sigma x plus y. Now, what I'm going to do is, with this knowledge of the new quantity, epsilon v, I'm going to sum both sides. And on the left, I will have sum of the normal strains, which is equal to epsilon v. And on the right, I will have 1 over E. And so let's have a look. So we're going to have a term like sigma x minus nu sigma x minus nu sigma x. So 1 minus 2 nu sigma x. For sigma y minus nu, 1 minus nu sigma y, 2 nu sigma y. And then for sigma z, we have a sigma z here, minus nu, again 1 minus 2 nu sigma z. So 1 minus 2 nu is like a factor, and then we have sigma x, sigma y, and sigma z appearing here. So now we have a certain combination of normal stresses coming from generalized Hooke's law, which governs, as I promised, the volumetric strain that we have just defined. But now we're going to go ahead and expand on this observation a little bit more, and we're going to do that by motivating a definition that is based on, again, this state of hydrostatic stress. So hydrostatic, so we're going to take something, immerse it deep into water, say into the ocean, into the Mariana Trench. Let's take a small cube of material, and it's going to be at a certain point deep in the ocean. It's going to be subjected, provided this cube is sufficiently small, to the same amount of pressure in all directions, which is P, right? So static, hydrostatic, because I'm not wondering, I'm not inquiring about the influence of possible water motion over this cube, which might change the stresses on one face with respect to another. No. So it's roughly the same pressure overall and sitting there in still water, let's say, right? So now, in this case, sigma x is equal to sigma y is equal to sigma z is equal to minus P, okay? And therefore, sigma x plus y plus z is equal to minus P times 3. In other words, if I take these quantities and sum them and then divide by 3, I would get minus P. And that minus P is associated with a state of hydrostatic stress, and that is the motivation for going ahead and defining the sum of the normal stresses divided by 3 as sigma H, which is called the hydrostatic stress. So this definition, the motivation comes from a state of hydrostatic stress, but the definition itself is valid for any state of loading, irrespective of the values of x, y, z. For normal stresses in particular, they don't have to be equal. They don't even have to be compressive. Okay, so with that, I noticed that the quantity here, which I have just calculated, is 3 times sigma h. And hence, I can conclude with these 3 discussions that sigma h is equal to E over 3 1 minus 2 nu times epsilon v. Okay, so now we have almost a relation that looks like a relation between normal stress and normal strain, but really this is the hydrostatic stress that is defined in terms of normal stresses, and this is the volumetric strain that is defined in terms of normal strains, and the constant in between is an elastic constant. It is a material property which is indeed exactly equal to the bulk modulus. Okay. And here is the idea of the motivation behind it being strictly something being positive, right? Because if I want to induce a positive volume change, I better have a positive, let's say, positive normal stresses on the block of cube, or in this case, the sum of the stresses, and therefore the hydrostatic stress is going to be minus B, so it's going to be negative. Volume change is expected to be negative as well, and B, therefore, better be positive. Okay, so that expression is now a rigorous derivation of the bulk modulus based on the generalized Hooke's law that we have introduced. Okay, so now again you can see that if nu is approaching 0.5, then this thing goes to infinity. In other words, even though you might be imposing relatively large hydrostatic stresses, because this is infinitely large, this is going to be infinitesimally small. In other words, almost negligible, like 0. So as a note, we make an observation that as nu goes to 0.5, the material becomes harder and harder to compress. In other words, harder and harder to induce a volume change for reasonable finite amounts of hydrostatic stresses. We call such a material one that cannot be compressed, or in other words, incompressible, no volume change. So, and that's because B is going to infinity. Okay, so this is also a nice example, but topic on its own, where we made use of generalized Hooke's law to derive a material property of interest. So next, we're going to solve yet another example that has to do with the generalized Hooke's law.